So the first thing we're going to go over is the types of chemical reactions, and there are 5 main ones that you need to know for now. The first is the synthesis and combination. So that's whenever you have 2 reactants making 1 product. A decomposition would be exactly the opposite, where you have one reactant breaking down into 2 products. A single replacement reaction is where you have some atom that's reacting with a compound, and then that atom becomes part of the compound, and then whatever else was in the compound gets booted out. So it's like a swap. The double replacement is a little more complicated of a swap. So for the double replacement, say I have 2 compounds. This reminds me of foil. The cation of one and the anion of another will bond. And then the other cation anion pair bonds, but it's always cation first. So it looks something like that. And then combustion is anything that reacts with oxygen, which is diatomic. And then you can get different types of products. It does always produce a lot of energy. Alright, so one thing before we get started with examples is when I converted this to the program where I can annotate on it, all my arrows became little rectangles and none of my subscripting kept. So we're going to have to kind of try to correct that as we go. Wherever you see a square, it's an arrow, and then numbers that are after letters should be subscript. So synthesis reaction is 2 separate atoms becoming a compound. So let's look at this example with the potassium and the chlorine. Potassium, which is not diatomic, reacts with chlorine, which is diatomic, to produce or yield a potassium chloride. So whenever you make the new product, you have to check the charges for yourself. The subscripts do not automatically carry. So the potassium is +1 and the chlorine is -1. So those charges cancel out without needing any subscripts. So the formula for potassium chloride is KCl. Period. End of story. There is no other formula for potassium chloride. Now that means that the formula is unbalanced, or the equation I should say is unbalanced, because there are 2 chlorines on the left and 1 on the right. So I'm going to need a coefficient on the right to make it be 2 chlorides. But that makes it now have 2 potassiums as well. So that's an easy fix over here on the left. Just put a 2 in front of the K. So we've got 2 potassium plus the diatomic chlorine yields the 2 potassium chlorides, or KCl. So just a couple more examples with synthesis. The first one is the calcium reacting with chlorine. So chlorine is diatomic, calcium is not. And so then I'm going to create a product, calcium chloride. Calcium has a +2 charge, chlorine has a -1 charge. So the crisscross here means that there's a 2 on the chlorine, which actually creates a balanced equation. Now I have 2 on the left, 2 on the right. So in this example, I do not need any coefficients, whereas in the last example I did because the subscripts were different. So the final answer there, Ca plus Cl2 yields CaCl2. And the charges are gone. For the sodium and the oxygen, sodium reacts with oxygen, and oxygen is diatomic, so subscript 2, yields, and we're going to make a compound with sodium and oxygen. So with sodium and oxygen, let me just do this on the side. Sodium is +1 and oxygen is -2. So when you crisscross there, you get Na2O for the formula for the sodium oxide. So put that in the equation and that takes care of the charges. So now I have a very unbalanced equation. I have 2 oxygens on the left, 1 on the right, and 2 sodiums on the right, 1 on the left. So I'm going to start with the oxygens. The 2 on the left means that I would need a 2 coefficient on the right to make that 2 oxygens. Now that creates a total of 4 sodiums. So I'm going to need a 4 in front of the Na on the left. I usually leave the lone atoms for last because they're usually easier to balance. So final answer there, 4Na plus O2 yields 2Na2O. So the next type of reaction is decomposition, and this is where you have a compound breaking down into its elements. The thing you have to be careful about on the product side is for your diatomic elements. So wherever you see it being diatomic, you're going to give it a subscript of 2. If it's not diatomic, you would just leave it alone. So let's look at the water example. H2O breaks down into hydrogen and oxygen. So hydrogen, is it diatomic? Yes. Oxygen, yes. So they both get a 2. Now it's unbalanced. Looking at the oxygens, I have 1 on the left, 2 on the right. So that means I'm going to need 2 waters. Well, now that creates 4 hydrogens. So where they come in pairs on the right, I'm going to need 2 molecules of hydrogen as well. So that's 2H2O yields 2H2 plus O2. So a couple more examples for decomposition. We're going to take our magnesium oxide, break it down into magnesium and oxygen. Is magnesium diatomic? No. Is oxygen diatomic? Yes. So I give it a 2. So whenever the subscripts are different, you're going to need to add coefficients to balance the equation. So we have 1 oxygen on the left, 2 on the right. So I'm going to need 2 MgO on the left. Well, now that creates 2 magnesium, so I'm also going to need 2 Mg on the right. So that's 2 MgO yields 2 Mg plus O2. For silver bromide, AgBr. Going to break down the silver and the bromine. So the silver, is that diatomic? No. The bromine diatomic? Yes. So we put a 2 there. So that creates an unbalanced equation just like above. So I'm going to need 2 silver bromides to make 2 bromine on the left to match the 2 on the right. That creates 2 silver. So again, we need a 2 on the Ag. So the single atom of B is going to try to replace X in this setup. So they're calling it a single replacement reaction because there's one thing trying to be replaced. So the atom that's alone is trying to become part of the compound. So A here would represent an anion, and B is trying to become part of the compound. So you see B with A on the right-hand side, and it boots out X. So X meaning X partner, so out of the compound. So if we look at our first example down here, we've got silver nitrate, where that 3 should be a subscript, reacting with magnesium. So the magnesium is trying to replace the silver. You would never have the cation replacing the anion. That would make a cation-cation compound, which doesn't happen. You would want the cation to replace the other cation so that the anion gets a new partner. So we're going to write magnesium with nitrate, our new partnership, and then kick out the silver. Goodbye, silver. So whenever we make a new compound on the product, just like we were doing on the last examples, we need to consider the charges. So magnesium has a +2 charge and nitrate has a -1 charge. So if you crisscross, you need 2 nitrates. So I'm going to put that in parentheses and put a 2 on the outside. For the silver, I just need to make sure it's not diatomic. If it was, I would give it a 2 on the bottom. But the only thing that comes up with is hydrogen, so usually not a problem. All right, so now this is a little bit more of a complicated equation to balance. So I would start with the hard part, the hard-looking part here, the nitrates. There are 2 nitrates. So I'm going to put a 2 in front of the silver nitrate on the left to balance out the 2 nitrates on the right. So now that means I need 2 silvers, and that's alone, so that's easy on the right-hand side. And then you do want to check your magnesiums. There's 1 of those on each side, so we are balanced. So our final answer, 2AgNO3 plus Mg yields MgNO3 with a 2 outside of parentheses plus 2Ag. So let's talk about this next one. Here, magnesium is trying to replace lithium. So it turns out there's a catch to single replacement reactions. Some things can replace others, where some things cannot. So what we have to check always is the activity series. We're going to go over that on the next slide, and you're going to see that magnesium is higher than silver, but lower than lithium. So here it cannot replace the lithium, but it can replace the silver. All right, so first thing I want to add in down here, it actually got cut off, and it's exactly what I'm trying to talk about, is the silver. It's actually below the mercury. Here you have the magnesium, and then the lithium's at the very top. So in order to replace something, it has to be higher to do the replacing. So can magnesium replace lithium? No. Can magnesium replace silver? Yes. So only if it's higher can it replace it. And you will be given the activity series on your test. You just have to know how to use it. So let's look at this one, where calcium would be trying to replace the magnesium. Remember, it's always cation replacing cation. So magnesium is lower than calcium, so we are going to see the calcium become part of the compound, and the magnesium now kicked out. Now that's the X. You do have to check your charges. Calcium is +2, oxygen -2, so those cancel out, no subscripts needed. Magnesium is not diatomic, so we're good there. This just should be an arrow. All right, so now on this one, silver would be trying to replace magnesium. Again, always cation replacing cation. The square should be an arrow. So the silver, as you saw, was at the very bottom of the list. Silver can't replace anything, so that's always going to be no reaction. Silver is trying to replace magnesium, but magnesium is higher. All right, so let's look at a couple more examples. First one here, we've got calcium reacting with silver chloride. So we're trying to see if the silver can be replaced by the calcium. We saw that silver was all the way at the bottom, so calcium is way on top there. It can replace the silver no problem. So we're going to get the calcium coming in to bond with the chlorine instead, and then kicking out the silver to the side, just to be by itself. So looking at the charges, calcium is +2 and chlorine's -1. So then we would need a 2 on the chlorine to balance the charges. And silver is not diatomic. That does make an unbalanced equation. Looking at the chlorines, there's 2 on the right and 1 on the left. So I would need a 2 in front of the AgCl. Now that also creates 2 silvers. So I would also need a 2 in front of the silver on the right. So Ca plus 2 AgCl yields CaCl2 plus 2 Ag. For the next one, we're looking at sodium trying to replace potassium in potassium chloride. And if you check the activity series, you can see that potassium is higher than the sodium, so therefore no reaction. So double replacement reactions are the most complicated of the 5 reactions. This is involving 2 compounds, and basically the cation and the anion of each compound swap. So here X would represent the cation of the first one. It would bond with Y, the anion of the second one. And B, being the cation of the second one, would bond with A, the anion of the first one. So then that would form B with A, cation first, and X with Y, using that kind of foil type of matchup. So let's look at the first one. NaCN reacting with H2SO4. So we would have sodium reacting with sulfate, Na and SO4, to make a new compound. So sodium has a charge of +1 and sulfate has a charge of -2. So to balance those charges, it would need to be Na2SO4 to get rid of the charges. And then the next compound would be hydrogen with the cyanide. But you always do cation first. So I'm going to write the H first and then the Cn. Hydrogen is +1. Cyanide's -1. That already cancels. So I don't need any subscripts there. So these can be really tough to balance. I would say consider the polyatomic ion as a whole instead of trying to break it down. So what I see is that I have 2 sodiums on the left and 1 on the right. And then my other problem is that I have 2 hydrogens on the left and 1 on the right. So I'll start with the sodiums since I saw that first. 2 on the left means I'm going to need a 2 in front of the NaCN. And then with the hydrogens, 2 of the H2SO4 means I need 2 H's on the right. Now that also creates 2 cyanides, but that's exactly what I did when I added the other 2. So that'll be the final answer. 2 NaCN plus H2SO4 yields Na2SO4 plus 2 HCN. Alright, so a couple more examples with this. I'm actually going to do the bottom one first since it's a little less atoms involved, might be a little easier to follow. So I've got sodium nitrate, 3 is a subscript, reacting with the potassium chloride. So I'm going to take the sodium and the chloride, cation from the first with the anion from the second, to make NaCl. So sodium is +1, chlorine's -1, so those charges cancel out. Then my next compound is going to come from the potassium with the nitrate. So we've got K and NO3. Potassium is +1, nitrate's -1, so those also cancel out. No subscripts. So if I don't have to add any subscripts, I know it's already balanced. But we can double check. I see 2 sodiums. I'm sorry, 1 sodium on each side. I see 1 nitrate on each side. I see 1 potassium on each side. And I see 1 chlorine on each side. So I am balanced. That's the final answer. NaNO3 plus KCl yields NaCl plus KNO3. All right, let's look at the one on the top. Calcium hydroxide, where that 2 is outside the parentheses as a subscript, reacts with Ag3PO4. So that 3 is a subscript on the silver, meaning there's 3 silvers, but that 4 is a subscript as part of the phosphate. So we're going to take our calcium and our phosphate, yes, including the 4, and make a new compound, CaPO4. And that one's a little tough to balance the charges. Calcium is +2, and phosphate is -3. So if you crisscross, you get Ca3, but then you've got to put PO4 in parentheses because that's what phosphate is, and then you're going to put a 2 on the outside of that. So let's do that down here. And then my other compound is I'm going to take the silver with the hydroxide, and I'm going to leave the 2 and the 3 behind. Those indicate the number of atoms or anions required to balance in the previous molecules. But the 2 isn't part of the formula for hydroxide. The 3 isn't what silver is on its own. So you're just going to bring over the Ag and the OH. The 4 was different because it was part of phosphate. So now we're just bringing over the Ag and the OH. So silver is +1. And hydroxide is -1, so those cancel, charges canceled. So we're good on just AgOH is the formula for silver hydroxide. So now I want to balance. So again, I would keep entire polyatomic ions together. So first thing I see, if I'm just kind of starting from the left, since there's a lot, is that there's 2 hydroxides. So that tells me that I would put a 2 in front of the AgOH. Meaning I have 2 silvers. But if I look over here, it's like I have 3 silvers. 2 silvers and 3 silvers. Well, what's the best thing that I can go ahead and go up to, which will accommodate kind of both of those things? It's kind of like least common denominator. I'm going to make it a 6. So I need 6 silvers. And if these comes in 3s, then I need 2 Ag3 would be 6 total. So now that's going to mess up the hydroxides that I just fixed. So now if I need 6 total hydroxides where they came in pairs, I'm going to need 3 calcium hydroxides to get to 6 hydroxides. And then as far as phosphates go, the ones that were connected back here to the silver, I have 2 phosphates. Well, I already had 2 phosphates. And if you check out your calciums, I already had 3 of those as well. So now I have it all balanced. 3 CaOH, where the 2 is outside the parentheses, 2 Ag3PO4 yields Ca3PO42 plus 6 AgOH. So a combustion reaction is defined as anything that reacts with O2, where the 2 is a subscript. So that has to be on the reaction side. It has to be pure regular oxygen gas. Combustion reactions typically produce a lot of energy. There's usually fire involved. What does fire need? Oxygen. So anything that reacts with O2 would be considered a combustion reaction. These reactions are always very exothermic, where they're producing a lot of energy. They actually are used a lot in engines. There's actually something called a combustion engine, producing a lot of energy. All right, so there is a specific type of combustion reaction that you have to memorize a little bit more about. So if I have a hydrocarbon, meaning it's made of only carbons and hydrogens, I don't know why the words are a little flipped there, but it's always going to be C something, H something, no O's, no anything else, if it's just carbon and hydrogen, and you have a combustion, meaning it reacts with O2, then your products are always carbon dioxide and water. So in terms of balancing it, there is a way to go in order that makes this a lot easier. So I'm going to react with O2, produce CO2 and H2O. So you see what's supposed to be subscripted there. So the first thing I would do is the carbon. So if I have 1 carbon on the left, I'm going to just have 1 carbon on the right. Not that you have to write that. If I have 4 hydrogens on the left, for water that comes in pairs, that means I would need 2 waters. So that's 2 H2O. Now that I have 2 oxygens also in water, that means, and then I have 2 oxygens coming from the carbon dioxide, so that's 4 oxygens on the product side. That's supposed to be like an O for oxygen. So coming in pairs, that would mean I need 2 O2 diatomic molecules. If you go to put the number in front of the O2 and you get a decimal, like 3.5, if you just multiply everything by 2, it'll fix that. It's a nice trick instead of having to go back and forth. Alright, so looking at the first example, I have magnesium reacting with oxygen. Well, we don't have products memorized for that, but that looks an awful lot like a synthesis reaction to me, so based on that, I can combine my magnesium and my oxygen. So my magnesium had a +2 charge and my oxygen -2, so those cancel. So that just means that it's unbalanced. So we're going to fix that with coefficients. 2 oxygens on the left, so 2 on the right. So that creates 2 magnesiums, so now we need 2 magnesiums on the left. So final answer, 2 Mg plus O2 yields 2 MgO. All right, the next one is a hydrocarbon combustion. So C2H6 reacts with combustion, so I know it's O2. Hydrocarbon combustion, I know my products are going to be CO2 and H2O. So if I do it in order like we talked about, carbon first. If I have 2 carbons, that means I need 2 carbon dioxides. If I have 6 hydrogens, since they come in pairs, I need 3 waters. So now I have 2 carbon dioxide molecules gives me 4 oxygens plus the 3 from the water, that's 7 oxygens on the left side. So if I cut that in half for the right side, I would get 3.5. But you can't have 3.5 oxygen molecules. So what we're going to do is double all of the coefficients. So the coefficients for the C2H6 was just 1, so 1 times 2 is 2. The 3.5 times 2 is 7. 2 times 2 is 4. And 3 times 2 is 6. So my final answer is 2 C2H6 plus 7 O2 yields 4 CO2 plus 6 H2O. So I know we did a lot of balancing equations in the examples already, just to do a couple where that's the only focus. We'll go over balancing equations a little bit. So you can see in the top example here where it's unbalanced, I have 2 oxygens on the left, 1, 2, 3 on the right. That's what they're calling unbalanced. So balance is where they add up to the same number on each side. So looking at just the oxygens again, now I have 4 on the left because this would be 2O2. And then I have 2 here and 2 there, so that's also up to 4. So now it's balanced. So we have to make sure that we're not adding in extra atoms or letting atoms disappear on us when we balance them. So the equations have to show how much of each molecule. This is what we're going to be calling the mole ratio when we get into stoichiometry next week. So our goal here is to balance so that you have the same number of atoms on each side of the equation. The law behind this, of course, is the law of conservation of mass. So the basic overview of how to balance an equation is to first make sure that you've got the correct formulas. So this is where we were predicting products, and that you have to check their charges. Once you've got that balanced molecule, you're done with the subscripts. So we're going to write that as reactants yield products, but sometimes it'll make it so that you have an uneven number of atoms. Do not change the subscripts. The charges didn't change, right? So instead you're going to use coefficients. Always double check at the end. Is it actually balanced, and is it the lowest ratio? Sometimes we go past the lowest ratio, which is fine. It still solves the problem, but don't forget to reduce it at the end. For example, if you had a 2 to 2 to 4 ratio, you would reduce that down to 1 to 1 to 2. So the biggest mistake, I say, is people taking the subscripts from the left and applying them on the right. The right is where the subscripts come from the charges. And then if they need to balance it, they cannot change. You have to change the number of atoms only using the subscripts. So subscripts and coefficient come from very different places. They're for very different things. So you never fix balancing with subscripts. Subscripts come from charges, and then coefficients are to balance. So we've got to keep that separate. Alright, so looking at this first example, we have iron reacting with our diatomic oxygen in order to produce rust, iron 3 oxide, Fe2O3. So we see we have 1 iron on the left and 2 on the right. We also see 2 oxygens on the left and 1 on the right. Couple pieces of advice here. If I see an atom alone, I like to leave it for the last because it's the easiest to fix. The other thing is oxygen is a problem more often than not, so that's a good place to start. And then starting with the oxygen, I can never make an even number odd, so the first thing I'm going to do is make this odd number even. So I'm going to put a 2 in front of Fe2O3 because the 2 and the 3 I'm going to try to get up to 6 like in the last one. So now that makes it so I have 4 irons. So I'll put a 4 in front of the Fe and 6 oxygens. So if they come in pairs on the left, that means I need 3 pairs. So the final answer is 4 Fe plus 3 O2 yields 2Fe2O3. Alright, so this next one, I have sodium reacting with water to form sodium hydroxide and hydrogen. So right now I have one sodium on each side and I have one oxygen on each side. So that sounds great. But then if we look at the hydrogens, I have 2 on the left and I have 1, 2, 3 on the right. So I'm going to fall back on that. You can never make an even number odd thing. So I'm going to try to make this odd number 3 over here become an even number. So I'm going to start with if the hydrogen molecule is already in pairs, I would make 2 sodium hydroxides. So that way I have 2 H's from each product for a total of 4, which is an even number. So how do I get 4 hydrogens on the left? Putting a 2 in front of the water. So that also makes it so that there's 2 waters in each place, since there was the oxygen in each of those molecules. So if I have 2 of each molecule, I again have 2 oxygens, which is great. So the only thing that's still a problem is the sodium. I have 2 now on the right, so I'm going to put a 2 in front of it on the left. So 2Na plus 2H2O yields 2NaOH plus H2. Alright, so for this one, we have a hydrocarbon, C3H8. Burning means it must be reacting with oxygen. So this now is a hydrocarbon combustion, O2. So my products I know are CO2 and H2O. So I'm going to balance with carbon, then hydrogen, then oxygen. So if there's 3 carbons on the left, I know I need 3 carbon dioxides. There's 8 hydrogens on the left, so if they come in pairs on the right, I would need 4 waters. So that gives me 4 oxygens from the water and 6 from the carbon dioxide for a total of 10 oxygens. So where they come in pairs on the left, I would need 5 pairs to get 10 oxygens. So C3H8 plus 5O2 yields 3 CO2 plus 4 H2O. So here I have silver nitrate, NO3, 3 is a subscript, reacting with copper. So anytime I have a single atom trying to react with a compound, I have to check the activity series. Can copper replace silver? Yes, it can. Silver's at the bottom, copper can replace it. So we're going to now have copper paired up with the nitrate on the right. Now copper has, it says it's a 2, so plus 2 charge, and nitrate has a -1 charge. So we're going to crisscross copper. The nitrate keeps the 3 in the parentheses, and then we have a 2 to represent 2 nitrates outside the parentheses. So we'll do that in the equation, and then show that the X is the silver. Kicked out the silver, which is not diatomic. So that's unbalanced. I would start with the bulky part, 2 nitrates. So then on the left-hand side, I would put a 2 in front of the silver nitrate. That means that there's 2 silvers. So on the right, show that there's 2 silvers. There's 1 copper in each side, which is great. So that's 2AgNO3 plus Cu yields CuNO3 with the 2 outside the parentheses plus 2Ag.